was only getting, let's say, 10 messages a second or 1 message a second, or maybe even, let's say, 1 message a minute, sure, I mean, I can just have one queue and it might still work. However, in a real system, what could possibly go wrong? Can you tell me, like, if you can think of, let's say, if you were designing a system yourself, what do you think can possibly go wrong in a messaging queue? All right, I see one response which is exactly correct. Single point of failure. That's one thing that can go wrong. And I think some of you are also saying the other part, which is bottleneck. So I'll go over both of these one by one. Absolutely correct. All of you are absolutely correct, right? So let's look at single point of failure first, and then we'll look at the bottleneck second, and we will solve both of those problems. Okay, everybody with me? Okay, let's see. Now, what is single point of failure? Imagine if my queue is only in one machine, right? Here is this machine. Let's say it's a laptop or it's a machine. I have stored the queue here. Let's say your message comes, goes to load balancer to maybe some machine, to maybe this database, and then gets pushed to this queue, this one machine. And then these services, your email service, your SMS service, all of these guys are reading from this one machine. Now, this machine, we would like to assume that it is permanent, it is Amar, but machines, the one thing you have to assume in a system design is machines can always fail. No matter how good machine you have, no matter how good electricity supply you have, things will go wrong in ways you can't imagine. So what that means is your machine can obviously die. It can die because maybe it rebooted, it restarted, maybe there was some system issue, something or the other could happen. Now, problem is here, if the machine dies, then there is no way, I mean, there is nowhere now I can store these messages, right? And very similarly, now my consumers cannot read these messages because the machine is dead. I can't contact the machine. So this one machine becomes a single point of failure. In fact, if it is permanently dead, then I might also lose all of these messages that I had here. If there was a hard disk failure, for example, let's say there was a fire or something, then I will end up losing all the messages here as well, right? Do you understand that? What I mean by single point of failure? Can I get a quick yes? Okay, great. By the way, this is a problem in any form of distributed system. If you store information anywhere, there is always single point of failure risk. Hence, you'll find the single point of failure risk in databases, in messaging queues, anywhere where you're storing information, there is the single point of failure risk. So hence, what do? You build redundancy. In fact, there is a video on CAP theorem. This is on Scalar channel. Just search for CAP theorem Scalar. You'll find a video. One thing which I would advise as a homework for all of you is go and watch that video whenever this session is done. Can you all please take a note? You will watch the video on CAP theorem once the session is done. Okay, great. Now, if you understand CAP theorem, then the second part that I'm going to explain will become much easier. Even if you don't, then I'll try to make sure that you have some understanding. Basically, one way to solve for single point of failure is that you have replicas. You have basically other machines that also store the same information. And there again, like if I have replicas, the problem becomes, how do I make sure there's this machine which has this queue? I have other machines that have the same queue. How do I make sure that these are always in sync? Hi, my name is Anshu. If there are 10 entries here, there are exactly 10 entries here. And there are exactly 10 entries here too. They are never out of sync. How do I ensure that? Now, to solve for that, how do I make sure that there is consistency in some ways in my replicas, the machines that have the copy of this information? I mean, there are master-slave architecture and multi-master architecture. I'll explain the simpler one, which Kafka also follows, which is master-slave architecture. And again, I will not be able to go a lot into depth of master-slave architecture, but I'll try to give you a very high-level understanding. Somebody has also posted rsync. Absolutely, rsync as well, but we'll not go into that much depth. I'll explain on a very high level conceptually. Look, in master slave, typically what happens is if you have multiple machines that are storing the same information, one of them is marked as a master, and the other machines are marked as slaves. So let's say slave number 1, slave number 2, and so forth. Now, all of the writes, so if somebody has to add anything to the queue, that will come to the master. The entry gets added here, and then master basically propagates this to the slaves. So writes go to master. Read. Now, if you want to, let's say, read an entry from let's say this queue, you can go to either the master or slave. Now, here, the reason why I mentioned CAP theorem to you is, depending on whether you want this to be highly consistent or available. And when you watch that video, you'll understand what is consistency, what is eventual consistency, what is availability. Depending on this choice, how the syncing up of master to slave happens, that gets decided. And there are a bunch of protocols which basically solve for either consistency or availability. The more consistent you want your systems, the more tightly consistent you want your system, the more complicated it gets. There are, for those of you who are interested, I mean, there is something called as PAXOS, PAXOS. You can go and read up on it later on. It basically tells you how consistency gets ensured when you have this multiple machine setup. There is also one question on is consistency tunable? Now, typically, if you have a multi-master system, again, for those of you who are interested, if you, for example, study Cassandra architecture, then you'll see in a multi-master setup, the consistency becomes tunable. Cassandra is a very, very classic use case of that. If possible, I'll see if I can share maybe some resources there on what tunable consistency means and how do you tune consistency by tweaking certain variables like number of machines that you have to read from when you're reading, number of machines you have to write to when you're writing. That helps you tweak consistency or tune consistency. But let's not deviate. I'm sorry for deviating. Very short answer. How do I make sure that there is no single point of failure? In fact, like, how does Kafka ensure that there is no single point of failure? It says, look, I will not store machine in a single machine. Sorry, I will not store the queue in a single machine, but rather I will have copies of the queue in other machines as well. The primary machine where this this queue is saved is called master. The other machines where I have the replicas, the copy of this queue is called as slaves. I also see that some of you are offended by the use of the word slave. I'm sorry, I didn't come up with that term. That's a term that is used in the industry for primary and secondary machines. Primary machines are called as master, and then the secondary machines are called as slaves. Okay. As I said, there is some reading that you could do. Here, a few things to keep in mind. We will discuss this in today's class, however, is there are cases where, let's say, master itself fails. Right? Now, if the master fails, then good thing is I still have these machines that still have my queue. So my read is not going to be affected. Because read can happen from any of the machines, right? So my reads can come to this machine and you can still read, let's say, what is on index 101 by going to any of the slave machines. And very quickly, a process gets started to select the new master. So one of these slaves gets selected as the new master. So that way your ride also might get affected for a very short period of time, but then they come back up very, very quickly. How master selection happens and how everybody knows who the new master is, we will discuss very shortly when we discuss Zookeeper. Is that okay with everybody? The master selection, how do people know that master is dead or new master has to be selected? How is the new master selected? How does everybody know who the new master is? All of that we will discuss when we get to the Zookeeper section. Okay? All right, sure. But takeaway from here, I will make sure that there are multiple copies of the queue, one in the master, others in slaves. Okay? Everybody with me now, till now? So issue number 1, how do you resolve with a single point of failure? Yes? Okay. Let's get to the second part, which is, all right, I have the bottleneck problem. What is bottleneck problem? Bottleneck problem is, in a way I'm saying, look, all of the writes have to go to the master. So that means there is only one master. There is this one machine with a queue. And on every message sent, you're basically adding one more entry to the queue. Another message, you add one more entry, and so forth, right? Now the problem is, if there are a lot of messages being sent, imagine, let's say you're designing this for WhatsApp or for Facebook Messenger, where like you're getting like millions of messages per second. Now, at the end of the day, this is just a machine, right? A machine can only handle so many requests at a time because it has limited amount of CPU, it has limited amount of storage, limited number of socket ports. So there are only so many requests that this machine will be able to handle at a time. For example, let's say, hypothetically, let's say it can only handle 10,000 requests per second. Now, what does that mean? That means that now this machine will start to become the bottleneck. Because I am getting million messages per second. But the queue where I can store this message for the consumers to consume can only take 10,000 requests per second. Which means 1 million minus 10,000, what do I do with that? So do you see how this master is becoming the bottleneck? Is the problem statement clear? That as I scale, if I'm designing it for very large systems, my master can become the bottleneck. So there's this only one machine where that queue is, and I'm writing all the messages in that machine. So how do I solve that? Okay, I see that some of you are already posting the answers. But before that, is the problem statement clear? Do you understand why I'm calling this a bottleneck? Problem statement clear. I'm not asking the solution. You can think of the solution in parallel, but is the problem statement clear? Okay. Just to explain to you your problem statement, right? Why do I say that a machine can only take limited number of requests? Look, when you buy a machine in the market, you figure out it has some amount of RAM. You figure out it has some amount of CPU. You typically see like some gigahertz of CPU. For example, let's say my machine has 1 gigahertz of CPU. That basically means it can perform 10 to the 9 operations per second. An operation is very simple, like just changing something in the register. Very simple operation with a bit is one operation. Which means my machine is going to run out of resources if you're making it do these many number of operations, more than these many number of operations per second. Now imagine if every request, I'm talking about CPU constrained request, right? Let's say if every request is making me do 10,000 ops, then even if the machine was not doing anything at all, the maximum number of requests that it can process at a time will be 10 to the power 9 divided by 10,000 roughly, which is 10 to the power 5, not more than 100,000 requests, because it only has limited CPU, right? Very similarly, you have RAM, right? RAM is how much you can store in your main memory. Now your RAM is also, for example, if you have 4 GB RAM, If every request is asking you to store, let's say, 200 MB worth of information, then you can only have 4 GB divided by 200 MB number of requests active at any point of time. So you see, like, one machine will always be constrained. It cannot take infinite number of requests. Do you agree with that? One machine cannot process infinite number of requests in parallel. It can only process some number of requests. How many number of requests depends on what does one request look like. How much CPU is it using? How much RAM is it using? From that you derive how many requests in parallel can I process. Okay. So I said I mean, I won't go deeper into how many what happens in every single request, but let's say if every machine could only handle 10,000 requests per second and I'm generating 1 million messages per second, then obviously this machine becomes the bottleneck. What happens to the remaining messages? Right? Now is the bottleneck problem clear? That this machine, my master machine, which has the queue, that becomes the bottleneck, because where do I write the remaining messages? Okay. So what do I do? Somebody also already mentioned that, oh wait, we can have topics and we can have partitions. But what is a topic? What is a partition? Let's actually understand that. Answer is correct. Yes, you can have topics and you can have partitions within the topic, but let's understand what it is. I'll go first with one example, right? You said, like, oh wait, there is a queue, right? But the question is, can there only be one queue? Can I have multiple queues? Let's see. Let's take example of Flipkart. Let's say I take example of Flipkart. Now in Flipkart, there are multiple kind of things that can happen. Somebody can buy an item. Is it fair to assume all of you know what Flipkart or Amazon is? Can I get a yes? You know what a Flipkart or Amazon is? Okay, great. Any e-commerce website, yes. Now you could go and buy an item on e-commerce website, right? Now if you buy, let's say, an iPhone, now you would have bought an iPhone, but there are a bunch of things that happen in parallel. If you think of what are the async tasks, look, your invoice gets generated. You get an email with confirmation that yes, you have bought an iPhone. Here are your order details. And the inventory also gets updated, right? Like number of iPhones that Amazon has or Flipkart has, that also gets reduced by 1. And there are a bunch of other things which you will also get an SMS, and maybe if you have WhatsApp enabled, you also get that. Everything happening in parallel, right? All of this is happening in parallel and in the background. Flipkart doesn't make you wait. It doesn't say, oh wait, I'm sending an email, I'm generating invoice, I'm updating the inventory. Till then, I will not confirm that you bought the iPhone. It's all happening in the background in parallel. Do you agree? So these are your background async tasks. The invoice generation or email sending, inventory, all of these is background async tasks. Now, very similarly on Flipkart, you could also leave a review. You can go on any product page and then write a review that, oh wait, this was a very bad product. And you can give it a rating out of 5. You can say it's 2 out of 5 or 1 out of 5, very bad product. Now, if you, let's say, leave a review, there also, if you imagine, there are a bunch of things that happen in parallel, right? Like the overall rating of the product gets updated. Maybe right now it was 4.2 out of 5. After your review, it becomes 4.1 out of 5. Please hold on to your question. I'll come to the question just after that. The second thing is, maybe there are these audit teams that get notified. Oh wait, customers are complaining about this particular item. Why don't we go and audit? So maybe there is a quality check that gets scheduled, but in parallel, in the background. Maybe there's an email that goes to the Flipkart team that, oh, somebody has given really bad rating. Maybe there's an email that gets sent to the consumer, the seller as well. Hey, look, somebody gave a very bad rating to your product saying this. Why don't you go and respond? All of that again happening in the background in parallel, async tasks. And so forth. Let's say if I'm chatting with the merchant, will have in its own async task, right? If you see, here the fact that somebody is buying an iPhone or somebody is leaving a review are two different items. Do they both need to be in the same queue? Can I have two different queues for, let's say, all events where somebody is buying an item and a different queue for somebody leaving a review? I can have a different queue, right? They don't need to be in the same queue. They can be in different queues. Why have the same queue, right? Because in a way, if I have a queue for, let's say, all people leaving reviews, then that will get, I mean, every time somebody writes a review, that will create an entry here. And who are the people who have subscribed? Oh, this rating service has subscribed, this quality check service has subscribed, this audit email service has subscribed. Very similarly, somebody buying an item could be a different queue. Who has subscribed? Invoice service has subscribed, email service has subscribed, inventory service has subscribed. So they could be two different queues. Which means even if, let's say, there are a lot of people buying items, that doesn't affect the review queue. It doesn't become a bottleneck for the review queue. So one is I am able to now, instead of one queue, now I have multiple queues. It still doesn't solve the problem fully. It makes the problem slightly easier, but it still hasn't solved the problem. So one is I can have different queues, but now how will Kafka know that I need to have a different queue for this, different queue for that? So Kafka says, wait, if you have two different topics, in a way, there's a concept called as topic. If you want different queues for two different things, just make sure they have different topic IDs. If there's a different topic ID, I'll create a different queue. Which means to say, when you say, look, I'm just posting a public, like hypothetically, right? You can say, hey, look, publish message. And you say, oh, wait, my message was something, right? Let's say message was some review. But here you can also pass a topic ID. This topic ID is, let's say, hypothetically 1 here. And then you pass something else. But when, let's say, somebody buys an item, then when I say publish message to Kafka, I say, oh, wait, let's say somebody has bought an iPhone, etc., etc. The topic ID is 2 here. If these two messages being published have different topic IDs, Kafka automatically will redirect them to different queues. They will not be there in the same queue. Okay? But the question is, fine, it reduces the load a little bit, but it is very possible that one of the topic is still getting a lot of traffic. It's getting a lot of messages. So for this topic, I still have the problem that I still need to solve. But I have segregated at least the topics in some ways so that one topic is not getting affected by the other. First thing, is that clear? Like, if I have different kind of topics, then I am making these topics independent. Now, one queue is not affected by the other. Just because suddenly there were a lot of people buying things, that doesn't affect my queue which was handling reviews. That will be calm and okay, and like it will get its reviews and it will notify its consumers. Right? Still hasn't solved the problem though. Just by the way, elaborating, Kafka internally will make sure that there is a different machine, different master for topic number 1 and a different machine with queue for topic 2. So if there are a lot of messages coming for topic 1, then yes, still this is a bottleneck, but at least topic 2 is not affected. Does that make sense? Are you with me till now? We still have to solve this. The problem is not fully solved. We still have to solve how do I make sure that if topic 1 is getting a lot of messages, I'm still able to handle that. But at least I have segregated. Okay, it seems like some of you are asking for a break. What we'll do is, don't worry, I mean, there is still a lot to be discussed in the class. We'll take a small break of 10 minutes. We'll resume post the break. There are still things to be discussed. Let me discuss what. We need to discuss partitions. Essentially, how do you remove the bottleneck? That is something we still need to discuss. We'll go deeper into Kafka architecture now. All of these concepts are cool, but then how do I go deeper into the Kafka architecture? What are brokers, and then how do you find out which machine to go to, etc., etc. We'll discuss details of that, and finally we will discuss. Actually, there's also consumer groups, and we'll also discuss Zookeeper. All right. We'll resume in 10 minutes. Again, I understand that some of you might feel that the session is slow. I'm so sorry. It's a large group, so I have to make sure that I take everybody along. So some of you might find it the right pace. Some of you might find it to be going a little fast.